Okay, today is the 15th of April, 2024. It's almost 9 o'clock and Pacific time, right? And let's continue with what we started last time. But before, let's take a look at this schedule here. So we can situate ourselves where we are right now. Okay, we had an exam last Wednesday. Today, we are going to continue with AC circuits. And if we finish, we will start with electromagnetic waves. Okay, and the next exam is going to be in May, 1 month, exactly 1 month from now, 15th of May. And let's see how many chapters we can cover until there, right? So more students coming. Here you go. Okay, here you go. Monday, 15th of April, 2024. Okay, and we start, remember, we're doing AC circuits. AC circuit. Okay, because in AC circuits, the current behaves differently. The current and the voltage, right? And the voltage behave differently if compared with DC circuits. Okay, the treatment is a little bit more complicated for circuits. Okay, the treatment ends up being a little bit more complicated. Okay. The only similarity is in the AC circuit that has a single resistor. Okay? Once we start using different elements, and different elements I mean capacitors and inductors, then adding, right? Using, different elements, capacitors and inductors, then the behavior of the AC circuit becomes rather different. Okay, that's why we start with a resistor in the AC circuit. Okay, that's why we start covering AC circuit with a single resistor. Because that's the simplest, because that is the simplest type of AC circuit. Okay? And so we're going to review AC circuit with a resistor again. And we're going to do that in a slightly different way than we did last time, which is going to be a more genetic technique. Okay? And I'm gonna tell you right away, very soon, is something that we already did that before for DC, and now we are going to apply that to AC, okay? So here you go, alternate current circuits, AC, right? Alternate current, I'm gonna put it AC circuit. Should be with a plural, circuits. Okay, so here you go, 3 different types of AC circuit. Oh man, 3 different type of AC circuit. Alternate, here you go. All right. So the first one is the alternate circuit with a single resistor. So the resistor is connected to a generator, a power supply that changes in time, a power supply that changes voltage sinusoidally in time. Okay, and how do we solve this type of circuit? Okay, we solve this type of circuit using the Kirchhoff loop law. So make sure that you learn Kirchhoff loop law, right? It's a very easy law to apply. And in this specific case, we have just a single loop. No, we have no junctions whatsoever. Okay. And we can apply Kirchhoff's loop law at any point in the circuit. Let's see here. View. I want to remove the grid lines better. So it can look better. It can look better. Okay, I'm gonna get the circuit and paste that in my notes. I don't like to do that because the file becomes very heavy when I add the pictures to the file. Okay, so here you go. AC. Okay, so here you go. AC circuit with a single resistor. And whatever principle I use here using Kirchhoff's loop law, okay, AC circuit with a single resistor. Okay. Using Kirchhoff's loop law. How do we do that? Let us use we start and starting, and starting at the negative side of the generator, we have the following equation. Okay, so we are going to go from the negative side here. We are going to jump to the positive, and once we jump to the positive side of the circuit or of the generator, right? What we end up having? We end up having, we do like that. Let's do step by step, right? V of the generator, right? Let's do like that. V of the generator. I'm gonna use that. Oh, I'm gonna use that later on. V of the generator. We're gonna pass through the resistance. And by the way, we have to also establish the direction of the current. It's not just like that. We have, so let's say at a given instant of time, we have a current. Okay, here you go. At a given instant of time, we have that you can put whatever direction you want. Okay, it doesn't matter. But we're going to choose the simplest type of direction. Here you go. Here's the direction of the current in the same direction of the loop, or the direction of the loop here. Okay, I want this one here. Good. Here's the direction of the current, and I'm going to label that I. Okay, and I'm going to copy that into my notes. Okay, so here you go. The current is flowing also in the counterclockwise direction. Okay, at this instant of time, this side of the resistor is positive, the other side is negative. As the current goes from this side of the resistor to the other side, it loses energy, it loses potential energy. So the next term in my loop law should be a negative V through the resistor. And then we are going back to the negative side of the powers of the generator, and you get a zero there, okay? And we continue this equation by substituting the value here for the generator, right? Here you go. The generator changes in a sinusoidal fashion. And we substitute the V sub R for the loop, for the Ohm's law, okay? Substituting, more students coming in, substituting V sub G for the voltage of the generator and V sub R for Ohm's law, we get the following equation. Okay, so here you go. We get the following equation. So what we want to do, we know the voltage, we know the resistor. What we want to find, we want to find the current, okay? So here you go, what I'm gonna do, treat that as an example, right? Example, find the current through the AC circuit, let's say, find the current along the above AC circuit. Okay, so treat that as an example. Solution. No? Given, let's do it this way, given V sub G and given V sub G, given V sub G and R, find the current along the above circuit, the AC circuit. Okay, so here we go. We're doing that. Now we solve for I. This term goes to the other side, and then we invert the sign here for this term. And we finally get this relation here. That's the more generic way of treating an AC circuit. Okay? And that's the simplest type of AC circuit that we are going to see out there. Don't forget, there are a total of there are infinite number of AC circuits that we can have, okay? There are infinite number of AC circuits that we can have. But now we're going to, let me copy and paste what we had out there. Here you go. Like I said, we have an infinite number of AC circuits out there. And I documented here the types of circuits. There are more, not just those, okay? But every AC circuit will have either a resistor, a capacitor, or an inductor, or a combination of all those three elements. What I have right in here, 1, 2, 3, 4, 5, 6, 7. I thought of 7 types of circuit, but that can have more. Okay? In this case, I'm assuming that the elements are all in series, but they can also be in parallel. So you can get things that are complicated, that's very complicated. But in this case, in the case of this course, we're going to teach only the simplest examples that we have. Okay, so here you go. So that's what we have. Okay, very important. The current here, note C, I'm going to put the V and VG and I next to each other, right? V sub G. Okay, so here you go. Note that the current has a sinusoidal relation, okay, which is exactly the same as for the voltage, okay? The current is directly proportional to the sine of 2 pi ft. The voltage is directly proportional to the sine of 2 pi ft, okay? In this case, because of this relation, because of the sinusoidal relation because the sinusoidal relation for both the current and voltage are the same, okay, are exactly the same, comma, we say that both the current and the voltage are in phase, okay, are in phase. Okay, they have exactly the same phase. And that is a nice way of illustrating the property of the voltage of the current in a graph. Let's see if I have it here for you. Oh yeah, right in here. Okay, that's what we call a phasor diagram. Okay, and is a very intuitive way of visualizing the variation of the voltage and the current as well in an XY diagram. Okay, this type, let me write here. These two types of mathematical relations can be visualized in a different way using what is called the phasor diagram. Okay? Phasor diagram. And the way we do that, let's start with the voltage first. Okay, here's the voltage. Okay, I will paste phasor diagram. Here you go, phasor diagram for the voltage of the generator. Voltage of the generator. Okay, so what we have right here, we have the maximum voltage that can be achieved in the circuit at a given instant of time. That's called V naught, right? And then we have the projection of this voltage along the y-axis. Okay, this voltage, this vector voltage here is making an angle 2 pi ft. Okay, and the sine of 2 pi ft times V naught is going to be exactly this voltage here that you see along the y-axis. Okay, and here is the omega t right here. That we know that this guy is moving in a circular fashion. Can you picture that? As time goes by, this vector here is rotating around the XY plane. Okay? It's a very intuitive way of seeing this type of mathematical relation. Similarly, we can have a similar diagram for the current. A similar phasor diagram for the current. And let's see, here you go. That's what we have as well. I'm going to copy and paste this one as well. Okay, that's okay. Phasor diagram for the current. Phasor diagram for the current of the circuit. Note, see that this angle here is exactly the same as this angle here. I wrote down 2 pi ft, but 2 pi f can also be written as omega, right? Omega t. 2 pi ft is omega t, okay? When we have this type of relation, when you, okay, here I'm gonna note, I'm gonna superimpose those two diagrams, right? Those two different phasor diagrams, they have here you go, better now. Oh, those two different phasor diagrams, and they're lined up with each other. They have the same phase. Okay, and here you go. Superimposing, right? Superimposing these two phasor diagrams in a single one, we have the following. Like that. There you go. Phasor diagram for both the current, for both the voltage and the current of an AC circuit, right? An AC circuit with a resistor. Because both the voltage and the current are lined up, are aligned. Both the voltage and current phasors, right, are aligned with each other, are aligned with each other. We say that the current and voltage are in phase, okay? Which does not happen whenever we introduce a capacitor and an inductor to the circuit. Okay, that's the important difference between AC circuits and DC circuits. That's an important difference between AC circuit and DC circuit. Okay, so now let's go for the next. The next one that I want to do is the capacitor. Okay. Now, example 2, right? Write the equation. Use let's see. Use the Kirchhoff loop law. Kirchhoff's loop law to find an equation for an AC circuit that contains only a capacitor, okay? So replace the resistor, right, with a capacitor of capacitance C. Use the Kirchhoff loop law to find an equation for this new AC circuit. For this new AC circuit. So here you go. Solution. Example 2. Now let's take a look at my new circuit. Here you go. No, that's a resistor, right? Let's go the one with a capacitor. That should be the one with a capacitor. Here you go. That's the one with a capacitor. And I'm going to put my current there again. So let's say at a given instant of time, the current in this circuit is flowing in this direction. Okay? So look what's happening here. You know, this generator is pumping the current in this direction, and this capacitor here, this plate of the capacitor is becoming positively charged. Right? Here's the loop direction that I already included here. Okay. As time goes by, this capacitor becomes charged and discharged, and the charge is inverted. Can you picture that? Hopefully I have one drawing here for that. So here you go. Yeah, I have it. So let's say we started at a given instant of time with very little charge in the capacitor, right? Current is flowing in the counterclockwise direction. A little bit later, the capacitor is a little bit more charged. The current is still flowing in the counterclockwise direction. Later on, you know. Oh yeah, the direction of the loop. See, the length of the loop illustrated the intensity of the current, okay? So a little bit later on, the intensity of the current also decreases. It decreases until the current becomes zero, okay? It is at this very point in time that the current becomes zero and the capacitor reaches its maximum charge. And then the current inverts the direction. Okay. And so on. Okay. So until it reaches zero. Okay. And so go back here to our illustration. Capacitor right here. I have my current set up there. I'm going to copy. Here's the capacitor C. Copy this guy and here's the circuit. Okay, AC circuit with a capacitor C. Okay, so just like before, we're going to use the Kirchhoff loop law. Okay, using Kirchhoff loop law, right? Exactly what we are doing, what we did before. Loop law, instead of the negative side of the generator, we have the following equation: V sub G. Okay, the capacitor, this plate of the capacitor is positive, and when we cross the capacitor, we get a lower electric potential. So consequently, we must have a negative V sub C. Okay, like that. Just like before that we did for the resist. Let me copy everything, right? Let me copy everything that we have here, and then I will use some of it. You know? because substitute VG for the voltage generator and VC obtained from the definition of capacitance. Okay, and how is the definition of capacitance? Remember what the definition of capacitance? Definition of capacitance is what? C equal to Q divided by V sub C. Okay, that's the definition of capacitance. Don't forget we have to substitute the V sub C here. Consequently, we have to pass the V sub C to the other side and the C to the other side. We get, what do we get? In the place of Ri, we're going to get Q over C. Q over C. All right? That's what we get here. And so we can do the following, you know? I'm going to replace, say, example 2. Find the equation for this new AC circuit and write, okay? And write the charge Q and the current I, okay? The charge Q is easy. Okay, to find the charge Q is easy, right? There's no problem here. So here you go. Right, all you have to do is to pass this term to the other side, multiply the whole thing by -1. Is that right here? Okay, there's no resistor here, right? Yeah, there's no resistor here. There's no resistor here. There's no resistor here. And just pass the capacitance term to the right side. And then we get the equation for the charge that's building up in the circuit. The charge is, you know, note C that the charge is in phase with the voltage, okay? But the same cannot be said, about the current, okay? In order to find the current in the circuit, we must use differential calculus. We must use calculus, okay? So it is at this point that you will have to memorize the equation for the current. It is at this point that you must memorize the equation for the current, okay? So remember that the current is going to be what? The current is going to be given by I delta Q over delta T. Okay, and everything else that is here must also be made delta Q over delta T. Delta, you know, delta must be made delta whatever over delta T, right? It's gonna be like that. Delta whatever over delta T. Okay, and then because those two terms are constant, we can take them out of that parenthesis. Okay, and if you apply calculus to that, what you're gonna get? You're going to get, you know, the term 2 pi f times cosine of theta. Okay. That's the part that you must memorize. The bold-faced result must be memorized. Okay? Everything else you should know how to do it. Everything else before, you must know how to do it. You must know how to do it. Okay? Notice now, if now I'm gonna put the voltage side by side, right? Just like I did before. But I'm gonna add the current as well. Here you go. We have the voltage of the generator. Here you go. I'm gonna put in order the voltage of the generator, the charge in the capacitor, how the charge varies. The charge in the capacitor is in phase with the voltage of the generator, but not the current. Okay, so here we go. Let me take out the bold face now. Yeah. And by the way, this expression here can be written down in terms of a sign as well, right? In terms of a sign as well. And we are going to do that. You know, let's continue here. Let's continue here. Okay, here we can replace by a sign, but then what do we do? What else do we do? We add a phase term of pi over 2 to the parentheses here of the sign, okay? And then I will write it here. There's more that we can talk about, but let's take a look at that first. Go. Okay. Now you can see that the current has a pi over 2 term in there. It's out of phase, both with the voltage and the charge. Okay, so let's represent this term here. We can call the I naught. I call it the I naught. Okay, let me write it down. I naught. It must be the maximum current through the circuit, right? And let's not forget that I naught is given by this thing here. Like that. And I'm going to take out the bold face. We usually put like a 2 pi f right in here. CV naught. Let's take a look at the phasor diagram of this one now. Capacitor, right? There you go. Okay, that was going to be the phasor diagram for the generator. It's going to be exactly the same as we had before, right? Because we're not changing the generator. So here you go. Phasor diagram for the generator, for the voltage of the generator. Phasor diagram for the voltage of the generator. We can even illustrate a phasor diagram for the current as well, right? We can do that as well. Here you go. Which ends up being phase. I'll put it here, Q naught. Okay. That would be the phasor diagram for the charge. And I'm gonna put a different color as well, so it doesn't, put this color here. And now I can phasor diagram for phasor diagram for the charge in the capacitor. Phasor diagram for the charge in the capacitor, right? It rotates. And now the phasor diagram for the current, the phasor diagram for the current is going to be 90 degrees off. We say that the current in the capacitor leads the voltage of the generator. Okay? And then we finally get, that's phasor diagram. Phasor diagram for the current in the capacitor, like that. And finally, we're going to overlap the phasor diagram of the generator and the phasor diagram for the current, the voltage of the generator, right? Okay, phasor diagram. Phasor diagram for both the voltage and the current of an AC circuit with a capacitor. You know, the current leads the voltage by 90 degrees. Simple enough, right? We can also add let's add the other one. Where's my, okay, this one here. And you're gonna add this one as well, but then I'm going to, one is going to be at the top of the other. The one that's going to be at the top is going to be the one that's shorter. There you go. So we can visualize it better. Send to back. Oh yeah, we send it to back. See that? Let's make it a little bit thicker so you can see it. Yeah, like that, right? Q naught. Okay. So that's the one I'm going to place there. Okay. The one I'm going to place in there. Here we go. Okay. Phasor diagram for the voltage, the charge in the capacitor, right? In the capacitor, and the current of an AC circuit with a capacitor. The current leads the voltage by 90 degrees, and the charge is in phase with the voltage. Like that. 90 degrees here. Capacitor. 941, we are in good shape here. Oh, there is one more thing that I want to tell you, okay? Very important. I'm going, and I will need to here write this equation that you see right in here. Not forgetting, do not forget One more thing about the current. The equation for the current. One more thing. Okay, I'm going to replace that here, right? We are going, what are we going to do? We are going to use using an analogous equation, analogous equation for Ohm's law, right? For Ohm's law, V equal to Ri, or I equal to V over R, right? V over I. We can rewrite the above equation and define a type of resistance and define a resistance for an AC circuit. We can rewrite like that. Here you go. I'm going to rewrite this equation, right? You know, now instead of having 2 pi fc here upstairs, I'm going to do the following. I'm going to put it downstairs, but I'm going to put downstairs in the proper way, right? It should be, this V naught should be divided by the inverse of this factor that you see right in here. Okay? And this term that you see right here downstairs, we call it a AC resistance. Okay? The term, you know, the term 1 divided by 2 pi fc has units of resistance, and we should call it an AC resistance, which is preferred in physics. Which is referred in physics as a capacitive reactance. Can you remember that? Which we abbreviate by the symbol XC, like that. Equal, or, you know, capacitive reactance. Capacitive reactance is nothing but an AC resistance. Okay, so here go. This capacitive reactance. Go like that. You can go ahead and do some dimensional analysis, and you're going to see that this ratio that you see here has a unit of ohms. Okay, doing doing dimensional analysis, it is straightforward to see that the capacitive reactance has units of ohm. I use units of ohms, okay? Okay, so I'm going to here write that in terms of the capacitive reactance. Okay, this guy here is here written as something like that. Okay. And now let's put that side by side. I'm going to put it here, I sub C to remind you that's the current through an AC circuit that has a capacitor in there. And then I'm going to put it side by side, the equation for the current of an AC circuit with a resistor. Okay, right in here. Right in here. Oh. And here I'm going to put, just to remind you that it applies to a AC circuit with a resistor. Note that the difference is just the denominator here and the phase term. That's 90 degrees ahead of this other one here, right? Next is for the inductor. 947 now. Let's do for the inductor now. All I have to do is to copy and paste what I did here for the capacitor. And you're going to have most everything, example 3. Almost everything that I wanted out of the way. Copy and paste it, right? There you go. That's example 3, right? Replace the capacitor with an inductor of inductance L. Inductance L. Use Kirchhoff's loop law to find an equation for this circuit, right? And write the current I of the system, okay? And now I have to replace this guy here with the inductor. Okay, current here. See the inductor L there? Current here. So let's say at this instant of time, we have the current in this direction. I can copy and paste right in here. AC circuit with an inductor L. Inductor L. Oh, inductor L. Here we go. Using Kirchhoff's loop law and starting from the negative of the generator, we have the following equation. Doesn't change anything, right? But instead of V of the capacitor, we're going to have V of the inductor. But in this case, the V of the inductor shouldn't be negative, but should be positive. Okay. And then we have using VG for the voltage of the generator and VL obtained from Faraday's law. Remember Faraday's law? We get. Okay, let's go back to Faraday's law. Remember Faraday's law, but the Faraday's law that used the inductance, not the other original Faraday's law. Faraday's law, let's see, that used the inductance. Let's find it. Let's find it. See here, right in here. Remember that? Okay, and then it should be somewhere right. Interesting. Okay, that's the one. That's the one right in here. Minus L delta I over delta T, okay? And we want okay, Faraday's law with the inductor term we get, okay? And then this one I'm going to put L instead of I and D, right? I'm going to put the L, I and D for the inductor, just to keep the that we do not need anymore. We get this one, this term doesn't change, but this term here changes. This term here does change. Okay? In this case, we can obtain delta I over delta T. Okay, let's add this term here. Replace the capacitor as an inductor. Use the Kirchhoff law to find an equation for this AC circuit. 1. A. Use Kirchhoff law to find an equation for the AC circuit with the inductor. B. Write delta I of delta T for the system. And C. Write the current I for the circuit. Here it should be delta I over delta T. Delta I over delta T. Okay, like that. Okay. So that's going to be A, right? That's going to be item A. No, that's going to be item A. This one right here. We get item A. Okay. Solving for item B. Solving for item B. We have the following. We start with this one here. Right? V naught goes to the left side. L goes to the right side, sorry. And we must also have a negative sign here. That's what delta I over delta T is all about. And then solving for item C, we have to integrate this equation here, okay? That's how we do with the calculus-based physics. You do not have to know how to do that, how to do this integration, right? But you have to memorize what is going to be the final result. Either memorize or refer it in your notes. We have the following. Okay. And the I ends up being something like that. Delta I over delta T is in phase with the voltage, but not the current. Note that delta I over delta T is in phase, that delta I over delta T is in phase, with the voltage. But same cannot be said about the current. In order to find the current in the circuit, we must use calculus. Right? It's at this point that you must memorize the equation for the current given, memorize the equation for the current given above. Okay. In this case, the current lags the voltage by 90 degrees. Okay. And I'm going to replace everything. Here goes side by side, right? We have this one doesn't change, right? This one doesn't change. This one is this one right in here, but this one ends up being something like that. In this case, I naught would be what? I naught would be 2 pi FL. 2 pi FL. Not C, but L. Where, you know, the reactive inductance is going to be given by this term. Okay. The term X sub L is called the reactive inductance. And we can write it down as like that, 2 pi FL. And now we have this table here. Oh, we still have to write down to display the phasor diagram, right? I'm gonna get rid of that. I don't need to show the phasor diagram for the generator again because you already know that, right? So, and now phasor diagram for the voltage, delta I over delta T. Delta I over delta T over delta T, and the current of an AC circuit is an inductor. The current lags the voltage by 90 degrees, and delta I over delta T is in phase with the voltage. Let's see if it's in phase. Actually, it's not in phase. Actually, it has a negative sign here, okay? So the right way of doing that is to state that delta I over delta T is 180 degrees off phase with the voltage. Okay? Make sense? Right? So this thing should be like that, you know? Minus can be either minus or plus, it doesn't matter. Minus pi can be plus as well, okay? So they're out phase, but they are collinear, okay? So here go. I'm gonna put, see, the delta I of delta T has this negative sign here. And because of this negative sign, delta I of delta T is not in phase with this voltage. It lags by 180 degrees. It lags by 180 degrees. You go. Minus, like that. Let's put I. And now I'm going to draw the phasor diagram for, okay, see, here's a a simulation, right? What happens to those phasors as time goes by, right? A given instant of time is here, time t equal to 0 is here, right? A little bit later on is here, a little bit later, and so on, okay? So what about here? Okay, right in here, that's what I want. Okay, that's the one I want. And I'm going to add this other phasor. Okay, and this phasor, I'm going to put a little bit longer, just like I did for the charge. Okay, I will change color. Okay, and label it delta I over delta T. Delta I over delta T. Symbol. More students coming in. Very soon we are gonna get our break. Okay, Corina. Okay. Here it's gonna be, WT minus 180 degrees. Minus 180 degrees. I'll put it in the color of the phasor as well. Okay. This one here, I'll put in the color of the phasor. Yeah, better. Let's put this one in the color of the phasor as well, red, right? And then I can copy. Those phasor diagrams are very useful, and you're going to see very soon why. They make our lives very, much simpler when it comes to a different type of circuit. Okay, and do I need more than that? Flags the voltage, 90 degrees here, delta I over delta T, and I don't need that anymore, right? Because I already did all of that. What else do I need to? Okay. Yeah, I'm gonna write down reactance, okay? Okay, this reactive inductance also have units of resistance. Now I can put everything side by side. Right? Let's put the resistance first, the current. Okay, I'm gonna state that the generator has this expression. Okay, and this one here is going. Yeah, I want to use the other one. Yeah, okay, I will do that. Is that simple enough to memorize it? It's not difficult, right? But don't forget, when I say that the current has this phase here, I'm saying that the current has this phase with respect to the voltage, okay? And I'm gonna put that here, sub L. Okay? The phase here, the phase term of the current of each device is written with respect to the voltage in the generator, okay? It doesn't mean that this current here is gonna lag this one by 90 degrees, by 180 degrees. It does not mean that this current here is gonna lag this one by 90 degrees. No, 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 no. It means that this current lags the voltage in the generator by 90 degrees. This current leads the voltage in the generator, okay? So it is I want to emphasize here, it is incorrect to state that IL lags IR by 90 degrees, okay? It's incorrect to state the following. It's incorrect that one, IL lags IR by 90 degrees. IL lags IC by 180 degrees. Okay? That IC lags IR, lags no leads, right? Leads IR by 90 degrees. This is incorrect. You shouldn't say that. Okay? Instead, the correct way to refer the phase of each of these currents is with respect to VG, the voltage. And now I'm going to IL. Here you go. I'm going to use it. IL right in here, IL right in here. And then IC right in here, IC right in here, and IR here, IR here. I'm going to state here. It is incorrect to state that because those are three different circuits. Okay? Those are three different independent circuits. A circuit with a resistor, another circuit with a capacitor, another circuit with an inductor. Okay? Now, when you combine a resistor, capacitor, and inductor in a single circuit, then you're going to see what's going to happen. Okay? You will see what's going to happen. And what time is that? 10:10 already. Wow. Okay, so time is flying here, right? Oh, what else do I have to do before we go to the? I want you to look at this table that I prepared for you, okay? This VG here is under subscript. Here you go. Here's the table. I'm going to put the table in the next page. Okay. AC circuits with a resistor, with a capacitor, with an inductor. Okay. Here are the relations for the voltage of the generator, right? Here's the current. The current is in phase with respect to the voltage. The current leads the voltage in the current lags the voltage. Phase difference is 0 plus 90 degrees minus 90 degrees, right? Current is in phase with the voltage, leads the voltage, lags the voltage. Voltage is in phase with, and that is important so you can understand, right? The current is in phase with the voltage. The current leads the voltage, yes. But what about the voltage? The voltage is in phase with the current. But because the current leads the voltage lags the current, right? It's a matter of referential here. Here I'm taking the voltage as the referential. Here I'm taking the voltage as a referential. Here I'm taking the voltage as a referential. But here I'm taking the current as a referential. Very important. The reactance, okay, the reactance of this circuit is going to be the resistance of the circuit. The reactance of the capacitive reactance is going to be this value here. The inductive reactance is going to be this value here. Let me see. This guy here is just repeated, right? Yeah, that's just repeated. Um, I'll leave it there anyway. It's slightly different because I substitute the value for the reactance, right? The terms for the reactance. So that's what we have. Let's go for our attendance first. And by the way, before you go into the attendance, very important here. Don't forget, I know see that most of you, okay, just reinforcing what I said before, right? One, I know that most of you did not display the proper number of significant figures in lab 3, okay? I mentioned that before, right? So I want you to do better, I want you to do, there's a little, okay. I want you to, because I want you to succeed in this course, in this course, I am giving you an opportunity to fix that in lab 3. So I postponed the deadline of the report of lab 3 till the day after tomorrow, okay? Okay, so make sure that you work on your display. So please make sure you display the proper number of significant figures in the spreadsheet. Okay, I haven't seen I have yet to see the significant figures for lab 4 and 5, right? Please do the same for the spreadsheet of the reports of labs 4 and 5. Okay. Don't forget the significant figures, right? And now what else? Okay, I also note that there are only 3 students doing the homework in Wiley Plus. Okay, please note that the homework accounts for 10% of your grade, and it may impact your final grade in a significant way. Okay, so I want to encourage you to do the homework online as well. Okay, so those are the important 3 messages that I am providing you. Also, don't forget, you can follow your temporary grade, preliminary grade, right? Preliminary final grade in Canvas, right? So I am inputting the grades that in Canvas, and I programmed everything in there so you can have an idea of your preliminary final grade there in Canvas. And what did I do? I also considered, as of now, your grade of the homework. Okay, this preliminary grade accounts for the grade for the homework grade you have so far, okay? The homework grade you have so far. So all those 4 points here. And what I'm gonna do, I'm gonna put here at the top. So, because this is an important message, right? I'm gonna put here at the top of this. Yeah, here you go. 4 important messages. 4 important messages. 1. In the spreadsheet, right? Of lab 3. I believe there only one group displayed the proper significance figures in there. We have 3 groups and the other 2 groups didn't do that. So I want you to encourage you to work on those significant figures. Otherwise, you're going to get a bad grade in the lab report, okay? So those are the 4 important messages that I have for you. Let's shrink this guy a little bit. Yeah, I shrank. Okay. Phasor diagrams, and this phasor diagram is going to become very important when we start to look for, when we start to solve for a circuit with a inductor, resistor, and capacitor. Okay. RLC circuit. That's what we have, and let's take attendance here. 10:20, almost 10:20. Yeah? Going here. Today is right here. Today is the 15th. Jacqueline, are you there? Okay, thank you, Jacqueline. Sky, are you there? I don't see Sky. Next, Ashley Izumo. Are you there, Ashley? Thank you, Ashley. Next is Corina Jurado. Thank you, Norberto Lopez. I don't see Norberto Lopez here. Vanessa Mena. Thank you, Vanessa. Yorgo.
Here.
Thank you, Lizelle. Thank you, and Paul Zapata. Thank you, Paul. So we have 7 students. That's good. Let me take a look here for the exam. Okay, good. So it's 10:20 right now. Break from 10:20 a.m. to 10:35 a.m. Okay. So I see you in 15 minutes. Hello, I'm back here. So let's take a look at the book. Wiley Plus. And let's see how he's doing the whole thing. So that's Wiley here. And let's also keep track what we have done so far. Let me get the Now, let's see. There was that little section of a previous chapter that I just covered. Okay, this one here. Remember that? Those guys were covering AC circuits in chapter 20. I don't think it's a good idea to do that. Before we can cover AC circuits, we must first cover Faraday's law of induction. And Faraday's law of induction comes after chapter 20. So I didn't think it was a good idea for the book to organize this material in this way. Okay. So, and let's see what we covered so far. Chapter 20E3, alternating circuits. Capacitors and capacitive reactance. We did that, right? Inductors and inductive reactance. And circuits containing resistance, capacitance, and inductance. Okay, so we already did 23.1, 2, and 3. Okay. No, sorry, we already did 23.1 and 2. We have to do 23.3. Okay. And there is also a straightforward way of treating that. I'm not planning to cover those two other chapters, okay? I'm not planning to those other two sections. So let's go ahead and go back here. 23.1. Capacitors and capacitive reactance. Capacitors and capacitive reactance. Okay, and what we have here, AC circuits. Then we have what? 23.2 inductors, and inductive reactance. And what else we have to do? We have to cover the other one. Circuits containing resistance, capacitance, and inductance. Let's do it this way. AC, the correct way would be to say AC circuits containing resistance, capacitance, and inductance. That's the so-called RLC circuits. Okay, this one is going to be we will call alternating circuit. Alternating circuit with a resistance, right? R circuit. We call it R circuit. Capacitance and capacitive in reactance. Okay, this one will be like C circuit, right? This one is going to be L circuit, right? And this one here would be RLC circuits. 23.4. Skip it. And the other one is 23.5. We're not going to cover that. Semiconductor devices. Then 23.5. Semiconductor devices. Skip it. The other one is resonance in electric circuits. Resonance in electric circuits. Maybe let's see, maybe I will cover it. This one, 23.4. Let's see how things go. May or may not cover, right? For now, let's skip it. May or may not cover. For now, let us skip. Let us skip it. Okay. Let's see. Capacitor and capacitive reactance. Here you go. Here you go, the same illustration that I did for you before, right? Yeah, very important. Yeah, I didn't cover the resistance. There is one more thing that I have to cover on those two circuits. Okay, and let's write it down. I didn't cover RMS yet, but I'm gonna do that. And this is a very important thing to have in mind. I'm going to emphasize that very soon. Okay, and here you go, frequency, right? And I didn't cover that, but I'm going to cover that. That's a capacitive reactance. And capacitor, okay, that's important to have too, is a graph. I didn't cover the graph, but you should visualize it but just by looking at the mathematical expression, right? One is for the voltage, the other is for the current. There's a 90 degrees difference between the phase of each. Okay, here you go. Here's the diagram, the phasor diagram, and inductors and inductive reactance. Inductive reactance, how it relates to each other, right? So here the phasor diagram as well. Okay. And the next one will be this one. Let me just go back here. Okay. Note C, note C from the table above that the reactance for a circuit was a resistor with a single with only a resistor is constant. Okay, I want you to concentrate on this part here of the table. Okay, the reactance is, okay, here you go, constant for a circuit with a resistor, constant and equal to R, right? For a circuit with a resistor. 2 is inversely proportional, right, to the frequency of the generator, right? See that? Inversely proportional to the frequency, and that's very important. It's very important that we have this relationship here. That the reactance is a function of this frequency, both in the for the capacitive reactance and the inductive reactance, right? Inversely proportional of the generator and linear, right? Or proportional or directly proportional to the frequency of the generator. Let's see, notice that for the reactance for a circuit with a resistor is constant, equal to R. Okay, let's put it this way. For a circuit with only, I'm going to emphasize only a resistor with only a capacitor is inversely proportional to the frequency of the generator, and a circuit with only an inductor is linear to the frequency of the generator. It's very important, this relationship here. Okay, and it will become clear. For now, I'm not going to explain why it's important. I will explain only when we come back, when we go back to only when we cover let's see. What you see right here is important right here in this section. In order to achieve resonance with those AC circuits, okay, we can change the frequency of our generator, okay? Not just change the frequency of the generator, but we can also change the capacitance or the inductance, okay, of the circuit. And that's what resonance in electric circuits is all about, okay? The above is important when we want to reach resonance with an AC circuit. This is very important in telecommunications, okay? The real life analogy is the case of your radio, okay? When you tune your radio towards your favorite radio station, okay? Basically what you're doing, you are changing the frequency, capacitance, and inductance of your device to reach resonance with the circuit of your, that your radio station transmit its signal. Okay, that's the importance of this chapter 23.3. You know, so the moment that you turn in your radio station in the knob of your radio, right? What you're doing, you're reaching resonance with your favorite radio station, and also TV station as well. It applies to TV stations as well, okay? That's the importance of this relationship here that you see. The resistor doesn't affect that, but the capacitor and the inductor, yes, they do affect that. Okay? And that's what's the importance of this section here, 23.4. I'm gonna both face them just to emphasize that we're not covering it yet. Okay. And what else do we have here that the book covered that we didn't cover? Okay, this graph here, which is exactly a visualization of those two graphs here, right? Those two graphs are in phase. This graph is a 90-degree phase difference, and this graph is also a 90-degree phase difference. That's what those graphs are all about. Okay, the current and the voltage. The peak here of the current is ahead of the peak of the voltage by 90 degrees. Ahead, no, it's behind. Sorry, it's behind. Lags. Okay, lags there. So we should take a look, and let's take a look of the capacitance. Yeah, here you go, the capacitance. See, leads by 1/4 of the cycle by a phase angle of 90 degrees. Okay. Yeah, I'm so what I'm going to do, I'm going to just plot it here in Excel so you can see the same graph that you have. See how I'm going to do that. This one right here, right? So here you go. Theta degrees, right? Theta in radians, and then sine of x. And then it's going to be sine of x minus 90 degrees. And I'm going to do sine of x plus 90 degrees. I'm going to put this one here that's leading, which is the case of the capacitor. Oh, okay. That's cell down. You go. So that would be for the case of a circuit with a resistor, the circuit with a capacitor, with the circuit for the inductor. Okay. And that would be the voltage, right? Of the generator as well. So here you go. Let's start at 0 degrees here. 5, 10, right? And I'm gonna go all the way up to 360. A full cycle. Here you go. Radian. Right? And now I'm gonna put sine here. I'm not putting the term that goes in front. I just want you to visualize the relationship. Here goes the plus 5, the relative. I just want you to visualize the relative graph of each one minus. Okay. And now we go here the graphs. Okay. And now I'm going to plot this term, this table here corresponds to the sine, right? And I'm going to do better than that too. Let's see here. View, freeze, good. Like that. I'm going to do like that. You know? I'm going to plot this one, and let's start with the capacitor. Right? So here you go. Insert chart. Okay. And did I put it plus 90 degrees? Let's compare that with the graph. Here's the voltage, right? And here should be the current for the capacitor. Let's see if let's compare that with the book, if it's the same or not. Yeah, it looks like the book made a mistake, okay? When I saw that, the moment I saw that, I noticed that there was a mistake, okay? But let's see if that's right or not. 90. Let's see. Let me pause momentarily here. Let's see if I did everything right here in my. Oh yeah, I made a mistake right here. I figured out. Okay, it's not pi, it's pi over 2, right? Because it's 90 degrees. So there is a mistake here, and there is another mistake here. So let's see if the book is correct or not. Which is rather unlike that the book is incorrect, but let's try it anyway. I have seen mistakes in books before. Let's see here. Yeah, okay, that should be pi over 2. That's good. That should be pi over 2. Okay, now let's take a look at the graphs, right? That's for the capacitor. Voltage and the current. Okay. Yeah, okay, the book is correct. Yeah, the book is correct. There's nothing wrong about that. Okay. The behavior that I have here is the same behavior that the book has there. Okay. And that again for the capacitor. If we do for the inductor, okay, we get this relation as well. So let's go back to the inductor. Yeah, that's the current. Okay. Whether the current lags or leads the voltage is better visualized by the phasor diagram. Okay. So let's go back here. Am I sharing? Let me see. Can you see my screen, by the way? Am I sharing the screen with you? Nobody said anything. I believe it's okay, right? Okay. Let's see, what am I doing here? Let's see, resume share. Okay. Okay, so let's cover it again. Okay, so let's do it. Okay, in a graphical sense, it's easier. Okay, it's easier to visualize whether the capacitor, the current of the capacitor lags or leads the voltage by using a phasor diagram. And when you plot, it's not that obvious at all because here we have the voltage, right? Here we have the voltage and here we have the current. It's not very clear whether the current is lagging or leading just by looking at this graph, okay? Lagging or leading the voltage. And that's for the capacitor. And now if we do for the inductor, we get something like that. That's exactly what we have there in the book, okay? What this one is for the inductor. Compare again. Here you go. Here's the current of the inductor as displayed in the book, right? That's exactly what I have here. And that's the current for the capacitor as displayed in the book. Okay, this one right here. Okay, start there at the top. Okay, so those are the things that the book did that I want to repeat here for you. And now we are ready to do, here you go, here's the linear relationship, right, of the inductive reactance with the frequency of your generator for the inductor, and also the capacitive reactance, okay, against the frequency. It behaves like that. And now we are ready to do the RLC circuit. RLC circuit. Circuits containing resistance, capacitance, and inductance. The book doesn't call RLC. The book called RCL. Most books out there call it RLC, okay? Most books. But this book called RCL. Okay, and how do we do that? Okay, that is a very important, very tricky way. Remember, I'm doing just RLC. I'm not doing RC, RL, or CL. The book doesn't do that either, so we stick to what the book is doing. Here you go. Here's my circuit, RLC circuit. Okay. Consider now an RLC circuit. I'm going to consider now an RLC circuit. An RLC circuit. AC circuit. That's the diagram, circuit diagram of an RLC circuit. Okay. Diagram of an AC RLC circuit. Okay. So now we are going to repeat what we did before. Okay. So that's going to be my example number 4. Example number 4. Okay. Now consider an RLC circuit, RLC AC circuit with non resistance, capacitance, inductance, and frequency F. Okay. Use the Kirchhoff loop law to find an equation for this new AC circuit with this new AC circuit. Okay. Here you go. Eventually, we will need to write the current for this circuit. Maybe, and let's see, write the current for this circuit. Okay. That's what we are going to do. And item A, applying Kirchhoff's loop law. Okay, what you're gonna have. So I need to copy everything that I did before. There you go. I'm gonna copy everything here. Okay. And we follow a similar script. We're gonna follow a similar script, okay? I'm not gonna use everything. Kirchhoff's loop law, we are going to have the following. Inside the negative side of the generator, we have the following equation: Fg of the generator minus V sub R for the resistor plus V sub L. And now we are going to have minus V sub C. It's minus V sub C because this side of the capacitor is going to be charged with positive charges, and this one is going to be charged with negative charges. Okay? That's what happens. Okay? And then there is a very interesting thing that's not understood very well by many people. There's a very interesting thing. Let's write down the equation first, and then I will VG, you already know that, here you go. Substituting VG for the voltage of the generator. VR using Ohm's law. VC using the definition of capacitance, right? And VL obtained from Faraday's law, we have, right? I'm going to write down each of them here. VR is the first one. VR is VRI. Okay? And I'm going to put the I sub R for now. VC is going to be what? Is going to be Q over C, right? Q over C. And VL we already have here. So our Kirchhoff loop law equation becomes, let's see here. And I have to write down the VG, okay? I didn't write down the VG, I'll write down it now. VG equal to that. All those equations that we need. Strange. Huh. Okay. Good. Now we're centralized here. We get item A. And item A becomes that. VG, VR, VL. I'm going to, and again, I'm going for now, I'm going to state, and here I'm going to state that that's the charging the capacitor, okay? I'm doing that. And you will understand why I'm doing that very soon. And finally, VL, okay? Okay, so this equation, you know, we have to solve this equation using calculus. There's no doubt about that, okay? That's how we solve this equation. But there is something even more important than that. There's something even more important than that. When we look at this circuit, okay, the current through each of those elements must be the same because it is a circuit that is in series, okay? So let's write that down, okay? Because all those elements in the circuit, because all the elements in the circuit are in series, okay? The current through all of them must be the same, okay? Must be the same. There cannot be a discontinuity in the current through each element of the circuit at a given instant of time, okay? The current right here at the resistor must be the same as the current right here at the inductor, which must be the same as the current just before the capacitor or just after the capacitor, okay? If those elements were in parallel, then the situation would be different, okay? The case would be different. through all of them must be the same. Okay? In other words, at a given instant of time, the current through the resistor must be equal to the current through the inductor and equal to the current just before and just after the capacitor. Okay? In other words, we must have the following. IR must be equal to I sub L. Okay? Must be equal to delta Q sub C by, right? Delta by delta T. Okay? This one here I call the IC, the current through the current just before the capacitor and just after the capacitor. Like that. Okay? This term here I call IC. And by the way, I'm going to simplify my notation by writing that all those currents are going to be equal to I. Okay? So the equation above becomes something like that. I here, and I just put Q. All right. I just put Q without the C in there. Don't forget that the Q is related to the current, right, of the circuit. Okay. In other words, the current passing through all elements must have the same phase with respect to each other. Okay? The same, okay? The same cannot be said about the voltage across each element. Okay, the voltage is going to be a different story. Okay, remember how the voltage and the current are measured, right? The voltage must be measured with a device that's parallel to each of those devices, with a voltmeter that's parallel to each of these devices, whereas the current is measured with a device that is in line here, that's in series with the whole circuit. That's why the current must be the same, but the voltage doesn't have to be necessarily the same. And that's where we come to the point that we have to adjust our equations, okay, for the voltage in terms of the phase that we got in the previous treatment, okay? So how does it go? Okay, it goes in the following way. We already know that the voltage across the resistor is in phase with the current in the circuit. We already know that. So, and And even more, let's do something else too. Let us write, let us write also that the current across, let's try the solution. That's exactly what we do, okay? Same cannot be said about the voltage across, okay? In other words, the current passes through all elements must have the same phase with respect to each other. So we can write the current through this entire circuit as, okay, RLC, right? Which is equal to I. It's going to be a voltage divided by a type of reactance that I call Z multiplied by a sine of 2 pi ft, okay? And we also know that the voltage across the resistor is going to be in phase with the current in the circuit. And we also know that the current of the capacitor leads the voltage in the capacitor. What does it mean? It means that the voltage must lag the current, right? And already inputted that here, okay? If the current leads the voltage, it means that the voltage lags the current for the capacitor, okay? That's why we had to do that treatment that we saw before. And the same reasoning applies to the inductor. If the current in the inductor lags the voltage in the inductor, then the voltage in the inductor must lead the current. Okay? And now we have this type of relationship. And now we go back, now we go back to our phasor diagram to find a final relation for the voltage and current. Okay, how do we do that? There's a very nice way of doing that. Here you go. And I have here for you. We are going to come up with a phasor diagram for the RLC circuit. Okay? So here you go. Let's see if I have it here. I started right here. RLC circuit. We start with the current now, with the phasor of the current now. Remember, the phasor of the current is the same for each element in the RLC circuit, which is rotating in this counterclockwise direction. We add the voltage across the resistor, okay? Which is also rotating in the counterclockwise with the current. And then we add the voltage of the capacitor, which must be lagging the current, right? And the voltage of the inductor, which must be leading the current. Put everything together in my graph, okay? We get this phasor diagram. It's not the final phasor diagram yet. We are almost there. See, the idea is rather simple. So here you go, phasor diagram for RLC circuit. Okay, I'm gonna copy and paste that into my notes. Phasor diagram for the final relation for the voltage and the current. Okay, here's the phasor diagram. Phasor diagram of a RLC circuit. Okay. I'm gonna erase that because let's see, I don't need that, right? What do we do next? We add those phasors vectorially. The VL we add vectorially. I was doing that like that. And I'm gonna put this, I'm gonna do it slightly different because I don't want this guy here in my drawing, okay? I'm gonna replace it here. Copy and paste, right? Okay. Next, we are going to sum vectorially the voltage phasors of the inductor and the capacitor. Okay. We go. Summing the voltage, summing vectorially, right? Summing vectorially the voltage phasors of the inductor and capacitor, right? And finally, we are going to sum those two other phasors vectorially, summing the VLC with the VR, right? Let's do that. Summing the VLC with the VR. One, two. What do we get? Well, we should be able to do that. Let's see. It's going to be something like that. Okay. I'm going to move this guy a little bit to the right. And we end up getting this. Fine, it's still not the final answer, but it is a very good way to start before we get our final equation, right? Final V RLC phasor okay, having an angle difference with the current phasor. Let's see here. This guy shouldn't be, we shouldn't have this one here, right? Shouldn't have this one here. Okay. I'm gonna put it closer. Let's get this one here, the right one. And now we have a phase difference here between this final voltage and the current phasor. Okay, and going back here, do we have let's see, yeah, I have the phi angle here. See that? And I'm going to delete that here. RLC. I don't need to have this one. I don't need to have this one. Okay, that's the one that I want in the final drawing. The question is how to get this VRLC and how to get this angle phi. It's not going to be difficult at all. Okay. Right there. Oh, going back here. I don't want that guy. Let's do it again. Okay. The final VRLC phasor having an angle difference with the current phasor. Okay. So we have, in this case, we are getting a phasor voltage that leads the current. Okay. That's what we are getting. Consequently, the current must lag the phasor diagram, the voltage phasor. Okay. And it's possible to calculate that. How do I find the VRLC? Okay, VRLC is easy, right? First, we got, we can see that this one should belong elsewhere. Let's take it. It should belong right in here. Right in here, right? Right? It should be, the VRLC should be what? I'm going to put, should be the phasor VLC square. Can you picture that? It's not difficult to picture, right? Plus the VR square, right? Which, by the way, is VL minus VC square. This is a right angle triangle, right? This is a right angle triangle. But let's not forget that the VL is going to be what? The VL, we're going to use Ohm's law again, but in terms of the inductive reactance and the capacitive reactance, okay? It's going to be capacitive reactance times I, inductive reactance times I, okay? And the resistance times I. Okay, we go ahead and what do we do next? We take the current outside this square root. The square, okay, there you go. Current. I'm going to put the current right in here in front of it. And what is left over here is another reactance that we call reactance Z. Okay, reactance Z, in which Z is given by this relationship right here. Right? Let's put it there at the end. Right? We should put there at the end. Right here. Okay. And then what else? Well, we can write down the following. We can write down, since we wrote down the voltages right here, right? You go, we wrote down the voltage like that, right? And we discover also that the current has a phase difference of phi. Okay. phase difference of phi, we can do the following. We can write down my current as a voltage V naught divided by the Z and a sine of 2 pi f. In that specific case, the current is lagging the voltage, right? So I can put a negative sign. But sometimes you can have that the current is leading the voltage. It's possible, okay? It's possible to have the situation in which the current is leading, and that applies whenever the V of C is greater than the V of L. So this phasor would be pointing right in here, and the voltage would be lagging the current, okay? The above applies whenever, whenever VL is greater than VC. VL is greater than VC, okay? However, when VL is greater than VC, is less than the VC, right? The phase should have a different sign, or here you go, I plus. So my genetic solution, so the genetic solution should be, here you go, like that. Yeah, plus and minus 5 for the current. And now we have everything, right? So here you go. We're doing here this example 4. Use the Kirchhoff law to find an equation for the new AC circuit, right? What else? B. Use a phasor diagram to find the net voltage of the circuit. The net voltage should be VRLC. 3. Okay, we found that, item A. Now, this one here is going to be item B. Item B, okay. Use a phasor diagram, use a phasor diagram to find the phase difference between the current and the voltage. And 4D, write the current for this circuit. Actually, we should do, this one should go before. And, right, gonna be like that. Item A, item B, and then that should be item C, right in here. Item C, and finally, item D. Item D. It's just a matter of doing trigonometric relations, okay? So that's how you have to do. Here you go. So here you go. The tangent of the angle phi. Just refer to this drawing right here. The tangent of the angle phi should be, here you go, right in here, right? We have V let's see, we have V, we should use this one here. Yeah, okay, that's the one. Okay, we have VL minus VC, that's the resulting phasor. Here is the angle. So this length divided by this length should be tangent of phi, okay? And that's what I have here. And I write that in terms of the current using Ohm's law. We obtain the inductance, the reactance, right? We know what the reactance is because we have F and FL and C, and that's what's going to be the phase angle between those guys, okay? And 1137, right? Let's see. How are we doing there? What else can we do? I want to finish it before going to the break. We are almost done with this chapter. Okay. Item C. Okay. Item. Okay. So I gotta erase this one here. Okay, good. So now we have our final, here we go. Final equations here. And I'm going to write down the VR, VL, and VC, right? So the final solution for the current and voltages are just okay. VR, the voltage lags by 90 degrees. The voltage across the capacitor lags by 90 degrees. The voltage across the inductor leads by 90 degrees, but it leads with respect to the voltage in the resistor. And what else? And the phi angle is given by that. Okay. You know, if VL, right, already wrote there. Okay, if VL minus VC is greater than 0, we use a minus sign, right? VL greater than VC, you use a minus sign. If it's VL less than VC, you use a plus sign. That's the final answer. What else can we do it? We can talk about the power as well. But I think I'm gonna take a break. Let's see, 40. No, let's go straight. Let's go straight to 12 o'clock. Okay. And let's talk about power now. Let's talk about power of an AC circuit. Okay. Recall that power of a DC circuit is given by, right? By that amount. VI, RI squared, V squared over R. We have the same relation for an AC circuit. The difference, however, we must be careful about the fact that both the V and I in a AC circuit is a function of time, okay? Is a function of time. For this reason, we use an average value for these quantities, okay? An average value for these quantities. A special, we're gonna use a special type, you know? Not exactly an average, but a special type of average value for these quantities. Okay? And let me clarify why is that. Okay? Let me clarify why is that. Recall that the voltage of my generator, right? Let's get the voltage of my generator here. Yeah, I will use this one and I'll just change the, here you go. Okay. Starting with the voltage of the generator is starting with the voltage of the generator. Okay, here's a generator. If we take the average value of the above function, we get 0 because we have a symmetric function with respect the horizontal axis, right? Let's go back there. There you go. Think about this. I'm gonna explain that. Think about this, and I'm gonna add more stuff here too. Let's see here. More oscillations to this guy. Okay. Think about this function here. Okay. Think about this function right here. Notice that the amount of time that the voltage stays positive is equal to the amount of time that the voltage stays on the negative side. Okay? Consequently, when we take an average of this function, of a sinusoidal function, cosinusoidal function, we end up getting 0. Okay? So here you go. Note C. I'm going to write that down here for you. Note C that the amount of time that Vg spends in the positive side of the axis is equal to the amount of time that it spends on the negative side of the axis. For this reason, the average value of this function is 0. Okay? Since a 0 value is not very useful for us, okay, we define a different type of average, okay? The so-called root mean square value, or RMS, okay? What is the root mean square value? The root mean square value is exactly what the name suggests. Okay? It is the average. It is the square root. It is the square root of the average of the square. Okay? That's what it is. So let me do. So in order to calculate that, comma, first we take the square of our function. Okay? And now when we take the square of our function, what happens? Everything here becomes positive everywhere, right? What was negative becomes positive. Don't you agree with that? Oh, it didn't do anything. This one here. Okay. First, we take the average. So first, we take the square of the function. And now that we took the square of our function, you can see that you no longer are going to have negative values here, but you're going to have positive values all the way down. Okay? And we can even plot that. Here you go. I'm going to do that sine square of x. Okay? Sine square here. Superscript. I'm going to square this value here, and I'm going to plot that for you so you can have a picture, exact picture of how it looks like. And now I'm going to plot this one, and just for comparison purposes, I'm going to put all of them in there. All right, here you go. Here's the square value of my sine function. And here's just my sine function. Now you no longer have negative values for this new function, right? So you can take the average it, and you're not going to get the zero. You're not going to get a zero. Okay? And when we do that, okay, so next, we take the average of the above function. We can do that using calculus, okay? So I'm going to, here we go. And the symbol for the average is the pointy bracket. This one, this pointy bracket here. That's the symbol of an average. We usually use that. And I'm gonna put the pointy bracket here as well. Here you go. Like that. Oops, not here. A little bit more. Here you go, like that. And there is a value, an average value for that is, we can go to the book, you're gonna see it. Go, it should be in that chapter that we over before electric circuits, right here, alternating current. Here, that's when they talk about the root mean square value. Okay, here you go. It's doing exactly what I'm doing. So that's going to be the peak power. Okay, and that's going to be the average value of the power. Let's see here. Oops, let's see. Okay, and but let's take a look at the root. Okay, the root mean square. That's what it is. Okay, the square root of 2. Okay, so what you end up having, the average value of this one here is gonna be, half of V naught. Okay, half of V naught. That would be the average value lying right in here for the voltage. Okay, so for the voltage, this average value is half. Okay, it's gonna be like that, but this term here is gonna be the half. Okay, so it's gonna be like that. It's gonna be V naught half times half. Okay, so let's just change. I'm gonna put an equal sign here. The same can be said about the current. Okay, the average value of the square of the current is going to be half of the current as well, like that. Okay, and then we have to have, so we square, we took the average of the square. Finally, is 3 steps. We must take the square root of the average of the square. Okay, square root of the average of the square. I see, like that. Okay, gotta fix that. And then we finally get the following. The root mean square value of the voltage is going to be, the square root of this term here. Square root of this term here, step by step, right? And the square root of this term is going to be V naught divided by, let's see, square root, no. Okay, gotta do that. By square root of 2. By square root of 2. So that's the idea of the root mean square value of any quantity. And we do the same for the current. Okay, here you go. But the current is like that because the current also changes sinusoidally. Okay. So the average, now we finally get that the average power right in here. The average power, well, I'm going to use this equation, this one right in here. Okay. And it's going to be like that. It's going to be because we have a square I here, we end up having a square root mean square value. The resistance becomes this term multiplied by the cosine of the phase of the angle. Okay. And that what we end up having for the power. Okay. And let's see here. Yeah, the book is not putting the cosine in there, so I'm gonna take it out. But strictly speaking, okay, let me remove that. Which, by the way, becomes this term here, multiplied by this term here, divided by 2. Okay, that what end up having the average power is in terms of the root mean square value. Okay, so what time is that? 11:58 right now. So if I ask you to calculate the power of a given circuit, just use this relationship here. The peak voltage times the peak current. Okay. And like I mentioned before, we are skipping sections 23.4 and 23.5 for now. 23.5 definitely we're not going to cover, but this one we may cover later on, okay? So 11:58 right now. If you don't have any questions, we can terminate it now and meet again on Wednesday. And don't forget about lab 3, 4, and 5 that are due on Wednesday, right? Let's take a look here. You go. Lab 6 is going to be, we're going to do lab 6 next Wednesday, resistors in parallel in a circuit. And again, lab 3, 4, and 5 are going to be due also as well on Wednesday. So I see you on Wednesday, okay? Thank you for being here. Hello, Yorgo, are you there?
Yes, Professor. I was gonna say, where can I access it? Do I look at
Okay,
modules?
I need you to turn on your camera
Okay.
first.
Okay.
Corina, are you there? Vanessa, are you there?
Yes.
Okay, do you have any questions?
Yeah, for the labs.
Yes.
For my format for lab 5, it's under like scientific notation for the R equation, and the R value is only showing up as 1. And I want
Okay.
to know if I'm supposed to change the format for that or leave it how it already plugged it in.
Which lab are you referring to? 3, 4, or 5?
To 5.
Lab number 5. Which group are you?
Group 2.
Group 2. So let's go there. Let me help her. Okay, you're going. Then we start. Let's see. Lab reports. Lab number 5, right?
Yes.
Again, what's your group number?
Group 2.
Group 2. Let's see. Raw data, group 2. I'm gonna share that with you. Group 2. Let me share the screen here. Let's see here. That's the screen here. Can you see my screen?
Yes.
Okay. So everything here is in scientific format, right? So what's your question?
My question is for my graphs. Once I plug it in, my regular equations, they'll show up in scientific
Format as
formation.
well. Okay.
Yeah.
Okay, so let me see. Let's see. We plotted, let's see, this one, for instance, right? Insert graph, right? I have to switch. I'm not gonna switch the axis yet, right? We still have to switch, right? Because I have to put the V in the vertical and the I in the horizontal. You did that, right?
Yes.
Let me see. Oh yeah, it's already there. Okay, the V is already there. We don't have to worry about that. And now what you're asking me is this notation here, right? In the X and Y axis, right? You want to know how to change it, right?
No, I changed it in my X and Y axis, but the way my equations are showing up are in notation, scientific notation.
Your equations, we mean the equations here for the trend line?
Yeah.
Okay, so let's see. Let's display that. Huh. Yeah, okay, let me see. This one shows in scientific notation. This one also shows in scientific notation, the slope.
No, just the y-intercept.
Okay, yeah, the
So it
y,
looks just like that. Yeah.
okay, yeah, the y-intercept you leave this way because you see that 10 to the minus 16. 10 to the minus 16 is a very small number. So you don't want to put 0.00000, right?
Yeah.
So leave this way. But then you might want to change this one here. This one, I need to see a number that's not one, okay? But the number that's very close to one. Do you see one in there?
Yeah.
Okay, so what do? You have to change that, okay? You click this box, right? Right click
Mhm.
this box, format trend line label, okay? You put number, and you start adding decimal places until you get a number that has that's not one. Okay, make sense?
Yeah.
Okay, so let's see how many decimal places. 5 decimal places. Yeah, that's 5 decimal places. I was lucky, right? If we
Yeah.
do like 3 decimal places, you still have one there. You do 4 decimal places, you still have one in there. So the least number of decimal places that's going to show a number that's not one is going to be 5 decimal places. Okay, 6 decimal places. Let's see, we can go even further. Okay, does it make sense?
Yes.
Okay, and did you make sure that you put all those numbers in, with the proper number of significant figures?
Yes.
Okay, here too, right?
Yes.
Okay, please do that for the lab 3, 3, 4, and 5. Okay,
Okay.
and that's a minute. Okay, that's it. Anything else?
One more question. How do we know when to do scientific or number format again?
Okay, I gave that rule of thumb, right? The rule of thumb for scientific and format. Numbers that are less than 0.001 scientific format. Numbers that are greater, right? That are greater or equal than, you put the numeric format. That's how you do it. And there's a good rule of thumb to use. Okay.
Okay.
After 3 decimal places, it's difficult to visualize the number, right? When I keep on
Yeah.
adding too much stuff here, it's so difficult to count those zeros, right? It's better to put in scientific format. Okay.
Okay. That was everything.
Yeah. Okay. Thank you.
Thank you, Professor. Have a great rest of your day.
You too. Bye bye.
Bye.
So let me check there. Let's see here. I'm going to adjust exam 1 for you. Exam quizzes. Exam 2. Okay. And let's see, edit. Questions. What time is it? 12:06 right now, right? Not everyone, but Just Yorgo. Today is 12:07. Let's put 12:07. Today is the 15th. I'm gonna put 12:08. So I have enough. No, it's not 12:08. It's 2:08. I'll put 2:09. Okay, so you guys give us a little bit more of time. 15, 12:09 p.m. and 15:09 p.m. Okay, so let's see if we have everything right here. 15, okay. You wanna save it? Huh? Let's see. Okay, check if you can visualize the exam.
Yeah, let me go back in it.
Let's see, attempt. Oh, I have to add one more attempt for you. Let me see how I'm gonna do that. One attempt, extra attempt. Okay. What about, can you see it?
Mm,
See now?
I'm going in it. No, it doesn't let me do it. It just says the last time, like 0 out of 31. It doesn't let me like redo it.
There is one attempt left. Don't you see it?
I don't see it on the side, no. Let me refresh.
Refresh it.
Okay, yeah. No, okay, now it's, let me do it.
Okay. Yeah, you should be able to start it right now.
Okay, yeah. Thank you, Professor. Okay, I
Okay,
see it.
keep your camera on, okay? And I will turn off my camera and my mic.
Okay.
If you need anything, just let me know.
Hmm? Professor, professor,
Yes, yes,
I want to ask for number two. I don't need to put no UF, right? I just put the digit number.
yes, just the numeric value,
Okay.
just the numeric value. Every question you put just the numeric value there, okay? Because I already mentioning the unit there.
Professor, I finished.
What did you say? What did you say?
I finished.
Ah, okay. Let me check.
Eh, yeah.
Don't go yet. Okay. So, okay. So do you have any questions?
No.
No? Okay. Okay, so see you Wednesday.
Hmm. Thank you, Professor.
Okay. Bye.